Hi, hello everybody. So this is the video dealing with section 2.6, rational functions and their graphs. And this is the first part of the video or of the section dealing with the definition and vertical asymptotes. So first, let's review what is the definition of a rational function. So a rational function, as you see here, is a ratio or quotient of two polynomial functions. So the official definition is Rx is a polynomial function if the numerator is a polynomial function and the denominator is a polynomial function, provided that the denominator function is not the value 0. Because if it is, we cannot divide by 0 and the result is undefined. Now, what is important to observe is when we have a rational function that we must understand that for whatever values that exist for x that cause the rational function to be undefined, those values, which we call roots, must be removed from the domain of the rational function. Now, what does that mean? It means that for whatever values or whatever polynomials we have in the denominator, we need to find the roots of the polynomial function by setting the denominator polynomial to 0 and solving for x. Those are going to be the roots of the polynomial. So those roots must be removed from the domain. So in order to do this whole procedure, the first thing that we need to be able to do is find the domain of any rational function. Now just remember that the domain of any function has to be written in interval notation. Okay? So this is a review from probably Math 119 or your previous course, where we look at rational functions. Here's example one taken from the book that you can verify the results later by setting the denominator to 0 in all cases and solving for x, finding the roots as we specified here, right? Setting the denominator to 0, solving for x, finding the roots, and then writing the domain of the function. Okay, so in the first case, example 1a, this is very easy. My qx is x minus 3. So in order to find its domain, I'm going to set it to 0 and I'm going to solve for x. Well, this is very easy. Just add 3 to both sides and we get x equals 3. Now, what does that mean? It doesn't mean the domain is just the number 3. It means that the domain is all real numbers except the number 3. So when you're graphing this, this is the real line. And here is the number 3. Let's say that the number 3 is right here. Okay, so let's say that this is x equals to 3. Notice that I have an open circle here. Okay, so the domain is every single number except this value. Now, why is that? Well, the reason that this is the case is because if I replace the denominator with this value 3, I will get 3 minus 3, which is 0. So then I have the numerator divided by 0, which would be undefined. So that's not possible. So the domain is going to become all of the region that is highlighted here except the number 3. So we write it in interval notation, negative infinity, comma 3, 3, comma positive infinity. Okay, so every number except the number 3. So remember the parentheses indicate that the number 3 is not included in the domain. Whereas if you had written bracket, the number 3 would be included. Okay, so we found the domain for the first function a, negative infinity 3, and 3 to negative infinity. All right, so let's do the second example. I'm going to erase this work right here. Let's do the second example. Same thing. My qx is the denominator, which is x squared minus 9. X squared minus 9. And I'm going to solve by factoring. I recognize this as difference of squares. So again, factoring techniques are required in this course, which were covered in your previous math course. So this will be x minus 3, x plus 3 equals 0. And then by the zero product rule, I set each factor to 0, and I solve it for x. This is the first one. This is the second one. Add 3 to both sides. Subtract 3 from both sides. So I got two values that must be excluded from the domain. So I'm going to draw the real line. Okay. So I am going to say that this is 0. And this location here is my -3. And let's say that this location here is my +3. Now, every value is allowed with the exception of these two. Okay, so I'm writing in blue. So my domain is everything in blue. So again, except this location and that location. Now, once I have the domain, all I have to do is write it in interval notation. So from left to right, -infinity to -3, -3, all the way to 3. Remember that 0 is okay. I don't have a problem when x is 0, right? So if you substitute here into the function 0 for x, I have 0 squared 0, 0 minus 9 minus 9. That's perfectly okay, right? Division by -9 is allowed. And then 3 to +infinity. So the domain of this function would be this particular set of values. Okay, so that's good. Now let's do the next example. So the next example, again, here's my qx. And in order to find the domain, I set it to 0. Okay. This is not difference of squares because of the plus. So the only thing I can do is subtract 9. And I get x squared equals -9. And at this point, you probably should be able to see that this, even if you take the square root of both sides, you get x here, but on the right side, you get -9, which is 9i squared, imaginary, which is plus or minus 3i. Now, this is not a real number. This is imaginary. Now, what does that mean? This means that this denominator or this function has no real roots. So what is the domain of this function? So the domain of this function is -infinity to +infinity. So all sets of values are okay. It is impossible for you to get a 0 in the denominator. And you can try that, right? So if you substitute 0 here, 0 squared 0 plus 9, 9. If you substitute -3, -3 squared is 9 plus 9, 18. And if you substitute 3, 3 squared 9 plus 9, 18. So it's impossible to get a 0, which means all sets of values from the real line are allowed. So the domain is -infinity to +infinity. So that looks good. Okay, so we have to be able to find the domain of the function. That's the first step, and be able to write that domain in interval notation as we have done it in Math 119. So that's the first step. The next step is we have to understand that that these roots are important for us to analyze something else. So, okay, so we're going to take a look at this now. So we are able to find the roots of the denominator, which are related to what we call vertical asymptotes. So we have to know, once we find the roots of the denominator, these roots have a special connection to something that we call a vertical asymptote. Now, the relationship is that the function is not defined for the roots of the denominator, but the function is defined as the x value approaches that root either from the right side or from the left side. And this behavior is called a vertical asymptote, right? As the function is approaching the root, it behaves a certain way. So a vertical asymptote is nothing more than this dashed line. There's four possible cases. This is what we call a vertical asymptote. It's represented by a dashed line. When the function approaches the root, the a values that you see here are the roots of the denominator. Okay? When the function approaches the root, either from the left side or from the right side. Now, and the function may be approaching the root from the right side going up, the left side going up, the right side going down, the left side going down. So here are the four possible cases. And we know that by evaluating the behavior of the function. So we can find the vertical asymptotes very easily. I'm going to show you how in a second. But then we're going to have to find the behavior. Which four possible cases do we have? Okay, it's going to be one of these four. So a vertical asymptote is a vertical line dashed, graphed in dashed format that the function approaches but never touches. And the reason that it never touches is because that would be division by zero, and that behavior is undefined. Okay, so now how do we find a vertical asymptote? So it's right here. How do we find a vertical asymptote? So if we have a polynomial, if f of x is a polynomial which has this form, px over qx, right? Both will have roots. How do we find these roots? We set px equals 0, and we set qx equals 0. And we find those roots. We find the x values that solve this equation. Now, if px and qx do not have any factors in common, whatever other factors remain are the vertical asymptotes. Now, I know the definition is a little bit weird. It's not just that we set qx to 0 and solve for x. We have to set qx to 0, solve for x, find all of the possible roots, and then make sure that these are also not the roots of the numerator. If, for example, I set qx to 0, I find these three roots, and one of the roots is also a root of the numerator, then this is not a vertical asymptote. The vertical asymptote is only the other roots of the denominator that are not roots of the numerator. Okay, we'll see an example right below. Okay, so this is the definition of locating and finding the vertical asymptotes. Let's see an example. Now, we're not going to be worried about if we have one of the four behaviors. Okay, all that we're concerned right now is finding a vertical asymptote. In a future video, which is, I think, it's going to be the third part of the video dealing with this section, is when we're going to graph these polynomials or these rational functions, and then we're going to be concerned which of the four possible cases we have. For now, we're just concerned about locating the vertical asymptote. Okay? All right, so let's take a look at the last examples. So finding the vertical asymptote, again, this is example 2 taken from the book, so you can check the results later. All right, so we are going to do the same thing as we did before, finding the domain, which is we're going to set the denominator to 0, and we're going to solve for x. So here's the denominator. We're going to factor as we did before. We already factored this exact same denominator, and we know set each one to 0 and solve for x. That means that the root coming out of here is 3. The root coming out of here is -3. Okay, -3. Now, normally we would say that this is a vertical asymptote and this is a vertical asymptote, but that's not enough. We have to check the numerator root. So how do we do that? Well, you set the numerator to 0 and you solve it for x. Okay. Obviously, this is already 0. And if one of these values equals this value, then that value would have to be eliminated as a root. In this case, obviously, 3 and -3 are not equal to 0, which means that x equals 3, x equals -3 are vertical asymptotes. Right. Another way that you can do this that may be a little bit faster is the following way. Okay. I'm going to show you a alternative that may be easier for you to see. Okay. The polynomial function is f of x. So instead of solving the denominator, setting it to 0 and setting the numerator to 0 and solving for x, what we are going to do is we are going to completely factor the numerator and completely factor the denominator. In this case, the numerator, there's nothing to factor, and the denominator, I'm going to factor it this way. Now, at this point, if there's anything that I can cancel from the numerator and denominator, I would. In this case, there isn't. If there isn't, you just set the denominator to 0, solve each case as we did before. So we get x equals 3, x equals -3. Now, since I already checked, they don't have any factors in common. These two values that I got here are the vertical asymptotes. So x equals 3, x equals -3 are vertical asymptotes. So this may be better. Several students prefer this method. Let's do this for the second case, g of x. So I am going to completely factor this, the numerator. I'm going to completely factor that, the denominator. And if they have any factors in common, I will cancel them. Okay. So let's see. G of x. So this is x plus 3. And again, it's the same denominator, so I already know how this is going to factor. -3. X plus 3. So notice in this case that the x plus 3 cancels with the x plus 3 from the denominator, which in this case, the only vertical asymptote would be this. I would set x minus 3 equals 0, and I would solve it for x. So I would get this. This is my only vertical asymptote. Okay, is a vertical asymptote. So notice that because there was a factor in the numerator here that matched the denominator. They cancel each other out. So the x plus 3 cannot be a vertical asymptote, right? So once I would solve this, I would get x equals -3. This is not a vertical asymptote. However, when we are to graph this g of x, okay, at x equals -3, there's going to be a hole in the graph. It's not an asymptote. It's not, the function is not, will not have a vertical dashed line, but there's going to be a hole here because at -3, the function is not defined, right? There is a hole in the domain. We're going to see this when we are ready to graph these polynomial functions. But for now, what we are trying to do is just to find and locate the vertical asymptotes. So if they have a factor in common, we cancel that and we just set the remaining factor to 0 and solve that for x, and that would be our vertical asymptote. Okay, the last case. Last case. Okay, x plus 2, x squared, x squared plus 9, right? So we are going to factor the numerator, nothing to factor, and we are going to factor the denominator. We can't factor because this is not difference of squares. So they don't have any factors in common. So in this case, as we've seen before, no vertical asymptotes because there is no division by 0. Okay, and there's not going to be any holes in the denominator here because we don't get a 0. Okay, obviously, if you put -3 here, you get a 0, but you get a 0 in the numerator. Okay, so when the function is a -3, I have 0, right? -3 plus 3 is 0, but the denominator is -3 squared plus 9. And as I said before, right, this is 9 plus 9, 18, it's 0. So there is no problem. There's no problem at h equal h of 3, h of -3. They're both zeros. Certainly there's no problem at h equals h0. Okay, so in this case, no vertical asymptotes. The usual case, let me just remind you, the usual case is this case where there are no factors in common between p of x, the numerator, and q of x, the denominator. Okay, so that's the usual case. A more complicated case is the second case, B, where there is a factor from p of x that is identical to q of x, and then you must cancel each other out. And then you're going to have one fewer asymptote than compared to example A. And then the least common case is the case where you do not have division by 0. You don't have any vertical asymptotes at all. So this is maybe not very common. This is the more complicated case. And this is the more typical case, case A. All right. So we should be able to, after this video, be able to find the domain of a rational function and be able to find the vertical asymptotes using this technique.